Ladies and gentlemen, good evening. This is the last lecture for this class, and also it will involve a topic which is very important. We will talk about the symmetric matrices and orthogonal diagonalization. You will see that the orthogonal diagonalization of a symmetric matrix is a diagonalization by means of an orthogonal change of coordinates. In this lecture, we will recognize and apply the properties of the symmetric matrices, also the properties of orthogonal matrices, and we would like to find an orthogonal matrix, let's say P, that diagonalizes the symmetric matrix A. Okay, so let's get started. At first, we will start talking about symmetric matrices. But before, so let me just say it. So symmetric matrices and orthogonal diagonalization. Okay, this will be the topic for today's lecture. And like I said, orthogonal diagonalization right, of a symmetric matrix okay, is a diagonalization by means of an orthogonal change of coordinates. Okay, and now we're going to ask ourselves the following question. Let me pose the following problem that we would like to answer in this lecture, which says the following: given an n by n matrix A, right? Under what conditions? Does there exist an orthogonal matrix P, and we will see what that means, an orthogonal matrix P, right, that diagonalizes A. So that is the question we want to answer. Right? Okay, and now let's start with symmetric matrices. Let's see the definition. And as you have already know by now, we have seen in chapter number 2 when we talked about matrices what a symmetric matrix is. But anyway, let's say that again. Let's recall the definition. A square, let's say, square matrix A is symmetric if when A is equal to its transpose, right? A is the same as A transpose. Okay, and now let's see some examples. matrices that are symmetric and of non-symmetric matrices. Let's consider the following matrices. And we're going to consider the 3 by 3. So this is 0, 1, -2, 1, 3, 0, -2, 0, 5. Matrix B is 4, 3, 3, 1. And the matrix C is given by 3, 2, 1, 1, -4, 0, and 1, 0, 5. Which of the following, which of A, B, C is symmetric? That is a question we want to answer, right? Okay, let's look at them. Well, the only thing we need to do right now is just to apply the definition. Let's do this. Let's look at A transpose. If we look at A transpose, this is nothing else than just 0, 1, -2, 1, 3, 0, -2, 0, 5. Well, guess what? It's the same thing as A. So it follows that A is symmetric. Okay, now let's look at B. We compute the B transpose. So B was 4, 3, 4, 3, and the second row was 3, 1. Well, as you can see, it's the same as B. Again, it follows that B is symmetric, right? And now let's look at the matrix C. Let's compute the transpose of this matrix. This would be 3, 2, 1, 1, -4, 0, 1, 0, 5. Wait. Yes, as you can see, it's not equal to C. So C is non, or let's say not symmetric. Sometimes we call the matrices that are not symmetric, we call them non-symmetric. Anyway, either of these two notions are work just fine. Okay, now let's point out some remarks. About this before we go and say a bit more about the properties of symmetric matrices with respect to their eigenvalues and eigenvectors and so on. Well, let's point out some remarks. And the first remark I want to point out is the following, is that a non-symmetric matrix may not be diagonalizable. Okay. The second one is that a non-symmetric matrix can have eigenvalues that are not real. right? For example, let's consider the following matrix. Let A be 0, -1, and 1, 0. This is a 2 by 2 matrix, right? And guess what? When we compute the characteristic polynomial of A, is given by PA of lambda. Well, if you compute it, so this is the determinant of lambda times the identity minus A, and this will be nothing else than just if you compute it, lambda squared plus 1. And the zeros of these, so the eigenvalues are given by lambda 1 is -I and lambda 2 equals I. Okay. So that's a very important fact, that the eigenvalues of a non-symmetric matrix might not be real. You will see that the next theorem, which we'll do, will tell us that the eigenvalues, all eigenvalues of a symmetric matrix are real. Anyway, another remark I want to point out is the following, is that for a non-symmetric matrix, the number of linearly independent vectors, eigenvectors, okay, corresponding to an eigenvalue, and this is important, can be less than the multiplicity of the eigenvalue. And I think we have seen an example when we talked about the eigenvalues and eigenvectors, right? Okay. And now the following theorem will be basically the most important theorem in today's lecture, one of the, if not the, and we will call this theorem, we will call this the real spectral theorem. Because we will see that this will give you some information about the eigenvalues of a symmetric matrix, and we want to see what happens to those eigenvalues. Okay, the theorem says the following: if A is an n by n symmetric matrix, then the following properties are true. Okay, and now let's see. The first one is the following. A is diagonalizable. So keep in mind that A is an n by n symmetric matrix. This is important. So we know that the symmetric matrix is diagonalizable. The second one, all eigenvalues of A are real. And the third one, if lambda is an eigenvalue of A, with multiplicity, let's say k, then lambda has k linearly independent eigenvectors. Well, that is the eigenspace of lambda has dimension k. This is very important. This is basically the most important theorem in this course. I'd like you to look at it. And now, well, I'm not gonna prove this theorem. This is a little bit more involved. I think this can be done in a more advanced, like a proof-based linear algebra course. But it's very important because basically it tells you what happens to the eigenvalues of a symmetric matrix. But we would like to prove that, in fact, let's prove it, but not for n by n matrices, only for 2 by 2. And let's do it like an example, as an exercise. Example 2. And well, we will prove that. So let's actually write it. Prove that that a symmetric matrix, and let's write it. Like I said, it's going to be a 2 by 2 symmetric matrix. So this will be A, C, C, B, right? This is the most general form, general way to write a symmetric matrix. So prove that this is diagonalizable. Okay. Okay, let's do it. And to prove this, well, I would like to look at the theorem. Let's look at we want to find the eigenvalues of A. So the characteristic polynomial of A is, let's write it. This is the determinant of lambda times the identity minus A, and this will be nothing else than the determinant of lambda minus A minus C lambda minus B. And the determinant of this guy will be lambda minus A times lambda minus B plus BC plus C squared, sorry. And if we do these computations here, this will be, well, it will be a quadratic polynomial. So this will give us lambda squared minus a plus b times lambda plus ab minus c. Okay, as you can see, this is a quadratic. The polynomial is quadratic in lambda. And now, well, we would like to solve this equation. So we want to solve the following equation, the quadratic equation. Lambda squared minus a plus b times lambda plus ab minus c squared, and this is equal to 0. The discriminant of this delta will be a plus b squared minus 4 times ab minus c squared, which if we do some computations here, if we carefully do some computations, this will be equal to, let's write it, a squared plus 2ab plus b squared minus 4ab plus 4c squared. Okay, great. And this will be, okay, a squared minus 2ab plus b squared plus 4c squared, which will be nothing else than just a minus b squared plus 4c squared. As you can see, the discriminant of this equation is the sum of two squares. So it must be either 0 or positive. Well, if this guy a minus b squared plus 4c squared is 0, right? Well, it's clear that it follows that a equals b and c is 0. There's no other way. So a is diagonal, is already diagonal, right? Okay, that is, let's write it. So we know that a equals b and c equals 0. This will imply that a will look like this. It will be a 0, 0, a. As you can see, this is a diagonal matrix, and on the main diagonal, we have the element a, the entry a. Now, if a minus b squared plus 4c squared is positive, then we can employ the quadratic formula. Then the quadratic equation, let's call this star. Then the equation star has two distinct real roots, or zeros if you want, if you're more used to this, right? Which means that, which implies that that A has two distinct real eigenvalues. Right? Has two distinct, let me be specific, real eigenvalues. Well, this implies that A is diagonalizable in this case as well. Okay, as well. And we're done, right? That's what we wanted to prove. We wanted to prove that any 2 by 2 symmetric matrix is diagonalizable, right? Okay, beautiful. Now, let me give you an example, since we're talking about symmetric matrices in the first place. The following example, what's the number? Example number 3, I think. Example 3 concerns the dimensions of the eigenspaces of a symmetric matrix. Okay. In fact, let's formulate it in this way, and we'll consider a 4 by 4 matrix. Find the eigenvalues of the symmetric matrix. Symmetric matrix A, and we'll consider a 4 by 4 matrix. Let's look at it with 1, -2, 0, 0. That's the first row. The second will be -2, 1, 0, 0. Okay. Then 0, 0, 1, -2. And now it's quite clear what to put on the, so it will be 0, 0, -2, and 1. Right? This is a 4 by 4 symmetric matrix. I'll leave it to you to see that this is symmetric. So A is symmetric. In fact, it's quite easy to see that A is the same as A transpose, right? So I'll leave it to you as an exercise to figure out this part, right? Okay. Now we want to find the eigenvalues of this, okay? And not just that, also determine the dimensions, and so the dimensions of the corresponding eigenspaces. Okay, so that's what we're trying to find out in this problem. So let's see. Well, when you have a symmetric, let me point out this fact that, again, that when you have a symmetric matrix, right, like we do have in this case, the 4 by 4 matrix, you should expect that all the eigenvalues are real numbers. Just like you have, we have previously seen from the real spectral theorem. Well, the characteristic polynomial of A is given by, and now let's write it. So this will be PA of lambda, which is determinant of lambda times the identity I4 this time, since it's a 4 by 4 matrix. Oh my goodness. And now let's write this crazy thing here. So it will be lambda minus, okay. So it will be the determinant of the following: lambda minus 1, 2, 0, 0. Actually, it's not that bad. 2 lambda minus 1, 0, 0. And then you'll have 0, 0 lambda minus 1, 2. And the last one will be 0, 0, 2 lambda minus 1. As you can see, this matrix it looks very nice. And the determinant of this, and I'll leave it to you as an exercise to show that so that I will not lose any time in computing this determinant, but I think I've done the computation somewhere here. Let me see. Okay, so this would be equal to lambda plus 1 squared times lambda minus 3 squared, I think. I hope yeah, that should be. You look at it. And now it's quite clear what are the eigenvalues. So the eigenvalues of A are, now I'm going to write lambda 1 is -1 and lambda 2 equals 3. Well, as you can clearly see that each of these two eigenvalues have multiplicity 2. Each of the two eigenvalues have multiplicity 2. Right? This is very important to know. Okay. Well, what do we know? By the real spectral theorem. So by the theorem, by the real spectral theorem, theorem above, I don't know if I yeah, I didn't, let's call it theorem 1. Okay. Okay, this is theorem 1. It follows that the corresponding what does it say? That the corresponding eigenspaces have dimension 2. Right? That's what the theorem says, the third part of the theorem. Well, let's be more specific here. In other words, the eigenspace of lambda 1 equals -1 has a basis of, and now we, I think I computed the basis here somewhere. I don't want to get into the details of this. As a basis of, okay, it was B1. This was, okay, so it was 1, 1, 0, 0. And the second vector was 0, 0, 1, 1. Okay. And the eigenspace of the second eigenvalue, lambda 2 equals 3, has a basis of B2, which will consist of the following. Okay, so it will consist of 1, -1, 0, 0, and the second one, it is 0, 0, 1, -1. Okay. Anyway, I will leave it to you as an exercise to check this. I've done the computations anyway, but you can just check this. So this is these are the two bases or the eigenspaces of each of the eigenvalue. Okay. All right, so okay, so this is how we well, these are just some things about the about symmetric matrices, and now we would like to talk about orthogonal matrices, and we'll see what's the difference between a symmetric and an orthogonal matrix. So orthogonal matrices, and you'll see that the situation here will get a little bit more involved, and you'll see that we will use notions from previous lectures about orthogonal vectors, orthonormal vectors. You will see how we are going to apply the Gram-Schmidt orthogonalization procedure. Anyway, to orthogonally diagonalize a matrix. But first, let's talk about the orthogonal matrices. And here, we will, like I said, we're veering towards orthogonal diagonalization, and we'll be interested in this. And let me remind you one thing. We said that when we diagonalize a matrix, right, a square matrix, we want to find an invertible matrix P such that P inverse times AP is diagonal, right? So remember that. For a square matrix A, we need to find an invertible matrix P such that this guy here, P inverse times AP, is diagonal, right? This is what what's all about the diagonalization procedure, right? This is what we did. Now for symmetric matrices, now the big question is, what happens when when the matrix A is symmetric? We'd like to see how are we going to diagonalize such a matrix. That is the big question we want to address. Well, for symmetric matrices, something happens. Well, the short answer is when A is symmetric, the matrix P can be chosen to have, let's say, the following property. And we'll see what this special property is all about. And let's write it. So this will be P inverse is nothing else than P transpose. In fact, this is what we call an orthogonal matrix. That's in fact the definition. And let's write the definition. I don't recall the number anyway. I'm not going to number it. A square matrix P is called orthogonal when it is invertible and we have this relation above. P inverse is nothing else than P transpose. Keep that in mind. That's what it means for a matrix to be orthogonal. That's the definition, in fact. Right? That's the definition. Let's see some examples. Quickly, let's see some examples. I don't recall the number of examples. Let's just cook up some matrices. Let me, for example, let's look at this matrix. I think I'll have some examples here. Okay, let's take a 2 by 2, 0, 1, and -1 is 0. Okay. Well, is this matrix orthogonal? Well, as you can, let's see. One, the determinant is 1, so one can compute the inverse. Clearly, P is invertible, the determinant is 0, which is 1, which is not 0. So A is invertible. Okay. And now we can use the formula with the adjugate or whatever by using the formula A inverse is 1 over the determinant of A times the adjugate of A. And remember that the adjugate of A is that matrix where you take the cofactor matrix, and remember that the cofactor matrix, how to compute it, and then you transpose the cofactor matrix. And in this case, so that we did not wait, P is invertible here, not A. P. And we're using this formula, right? We get that P inverse will be nothing else. So you want to use, in fact, let me just, I don't want to change the notation here. Let me stick to P. So P inverse, return of P times the adjugate of P. Anyway, by doing all these computations, you will find that the P inverse will be nothing else. Well, let me just look. I have the computation. So it's 0, -1, and 1 is 0. And clearly, this is nothing else than just P transpose. So again, it follows that P is orthogonal. Now let me give you another example. Another example of an orthogonal matrix, and this time let's take a 3 by 3 matrix. And I think I have the computations here anyway. I'll just mention the matrix. The matrix let's just say this time the matrix P, and I'm gonna take the following 3 by 3 matrix. Okay, so we'll have, let's say 3 over 5, 0, 4 over 5, okay, 0, 1, 0, and the last one is negative 4 over 5, 0, 3 over 5. Okay. Well, I will leave it to you as an exercise to show that, check that the inverse, well, of course, you need to compute the determinant first and so on, that the inverse is nothing else than 3 over 5, 0, 4 over 5, 0, 1, 0, and negative 4 over 5, 0, and 3 over 5. Okay, well, it's easy to see that this is actually the P transpose. And this guy here, it will be a little bit of an exercise for you. By now, you already know how to compute the inverses of matrices and so on. We have seen this plenty of times. I think we have seen this in the midterm exam. There were plenty of ways of computing the inverse of a matrix. Okay, so these are two examples of matrices two examples of orthogonal matrices. And now I want to delve a little bit more into details about the properties of orthogonal matrices, and this will be described by the following theorem, which the number, I don't know. Anyway, theorem, I hope I don't have to recall it by the number, which says the following: an n by n matrix P is orthogonal okay, it's orthogonal if and only if let me write it in this way, its column vectors form an orthonormal set. This is very important. And now, given this theorem, we will go back to what we have learned in previous lectures. Anyway, I'm not going to prove this theorem. It's the proof is not hard. Basically, you just have to write the matrix P, and you write. In fact, let me just explain it a little bit. So the main idea of the proof of this theorem is the following: you write the matrix P as in this way. Let me write this column vectors P1, P2, Pn. And now what I'm going to do, well, you can write this explicitly as a matrix, and then you multiply by the transpose of P, and then you'll look at this set P1, P2, Pn. You'll see that is orthonormal because any two columns, you'll see them as vectors, are their dot product is 0, and they're unitary. So that's very easy to see. In other words, you will see that this guy will be nothing else than just the identity. So from here, this will imply that P transpose is nothing else than just the inverse of P, well, which is exactly the definition of P of an orthogonal matrix. Anyway, like I said, it's if and only if. You can also do the other way around. It's just you reverse all the steps and you go back. We go backwards, and And there you go. Okay. So I'm not going to dwell too much on the proof of this theorem, but I'm going to dwell on another example, example number, should keep the numbers here because, okay, this is 4, this is 5. Example 5, we want to look at the following matrix. I think I've noticed somewhere, anyway. We want to show that the following matrix, that the matrix P, which will be given by, again, I will take a 3 by 3, but this will be a little bit more, okay, more pretentious. So it will be 1/3, 2/3, 2/3, okay. And now here we go. Brace yourselves. The second one is -2/√5, 1/√5, and 0. And the third one is -2/3√5, -4/3√5. And the last one is 5/3√5. Oh my. Okay. That's my 3 by 3 matrix. We want to show that this matrix is orthogonal . Okay. And well, of course, by showing that P transpose is nothing else than just P inverse, and probably don't need that for computations. And then we want to show something even more, then show that the column vectors of the matrix P form an orthonormal set. Okay, so let's look at the problem. Now, probably I'm going to need the notes again for some computations, but anyway, it's quite clear what to do. First, we look at this P, we multiply P by its transpose. Let's write it. It will be 1/3, 2/3, 2/3. -2/√5, 1/√5, and 0. And the last one will be -2/3√5, -4/3√5, and 5/3√5. And we're going to multiply this by its transpose. So let's write it. It's going to be 1/3, 2/3, 2/3. -2/√5, -2/3√5. Right, the second one will be 1/√5, -4/3√5. Now I have here 0 and 5/3√5. Okay, so let's multiply these two. Well, it's quite clear what is the result. Anyway, when you multiply these and you add them, you have 1/3 times 1/3. This will give us nothing else, and I'll leave it to you as an exercise. This is the identity. So I'll leave it to you as an exercise to show that this is the identity. And since P transpose is the identity, well, if you multiply by the inverse to the left or to the right, to the left, sorry, it follows that P transpose is nothing else than P inverse times the identity, which is P inverse. So P is orthogonal. Okay, that was easy to see. And now let's look at the second part is to show that the column vectors of P form an orthonormal set. We need to show this. Okay. Now let's look at these column vectors of P. Of the matrix P are given by the following. Let's write them. Okay. The first one is P1 is 1/3 -2/√5 -2/3√5. Let me write this. Okay, that's my first vector. P2 will be 2/3 1/√5 -4/3√5. And the last one, P3, will be nothing else than just 2/3, 2/3, 0, and 5/3√5. All right, beautiful. So these are the three column vectors of my matrix P. And now, well, guess what? Let's look at the computation. We want to show that this is an orthonormal set. Well, we need to check what? We need to check two things. We need to show that these three vectors are mutually orthogonal, right? 2 by 2, basically. And we need to show that they're unit vectors. So let's see that. P1 dot P2 will be what? Will be 1/3. Let's actually do the computations of one of them, times 2/3 plus -2/√5 times 1/√5 plus -2/3√5 times -4/3√5. Well, and if you do the computations here, so this will be 2/9, oh my, plus, okay, minus, sorry. Um, 2/5 plus this would be 8/9 times 5. And guess what? By computations here, this will give us 0. Anyway, similarly, P2 dot P3 will be the same as P3 dot PU, and it will give us 0. Moreover, we have the following. We have that the norm or the length of P1, which will be, in fact, let's compute it, should be the square root of 1/3 squared plus -2/√5 squared plus -2/3√5 squared. The square root of this will give us, well, if you do the computation, it will give us 1. And the same happens for the length of P2 and the length of P3. Since we, so let's check this. This implies that that the set consisting of P1, P2, and P3 is an orthonormal set. And keep in mind, we have used by the above theorem. In fact, let's denote it by something now. Theorem 2 by theorem 2. Right, by the previous theorem, that when we said that an n by n matrix P is orthogonal if and only if its column vectors form an orthonormal set. Okay, so this is just an application of that theorem, right? Okay, now let's see what let's see what else should we do before we go to orthogonal diagonalization. Before talking about orthogonal diagonalization, well, we should say a few things about the properties of symmetric matrices, and I want to say a little bit more about the eigenvalues of symmetric matrices, and moreover, more about their corresponding eigenvectors. So we have the following theorem, and this time I should be careful to number it. It's theorem 3, which is a very important property of symmetric matrices, and it says the following: let A be an n by n symmetric matrix okay, if lambda 1 and lambda 2 are distinct eigenvalues of A, of my matrix A, okay, then their corresponding eigenvectors, let's say x1 and x2, let's call them like this, guess what, are orthogonal. This is important, very important theorem. Basically, I have a matrix, a symmetric matrix, and their eigenvalues, the corresponding eigenvectors to the distinct eigenvalues of my symmetric matrix are orthogonal. Well, the proof of this is not hard, but anyway, I don't want to get into the details about it. Well, we just write the definition, you write the properties of the dot product, you use the fact that A is symmetric, and everything just it's just computations, and it follows from there. Okay. Now let's see an example. Example number 6, I think. Oh, yes, number 6. Which says the following. Now let me consider a 2 by 2 matrix this time. Show that 2 by 2 symmetric matrix, of course. Okay. Show that the two eigenvectors of the following matrix, I'm going to consider 2 by 2, And let me take a simple 3, 1, and 1, 3. Of course, this is a 2 by 2 symmetric matrix. That's obvious. A is the same as A transpose. Show that the two eigenvectors of this corresponding to distinct eigenvalues are orthogonal. Okay. We want to see the truth of the above theorem through this example. Well, we need to compute first, we need to compute the characteristic polynomial of A. Is PA of lambda is nothing else than just the determinant of lambda times the identity minus A, which will give us lambda minus 3 minus 1, lambda minus 3. And if we compute the determinant here, which is quite easy to do, so 2 by 2, this is lambda minus 3 squared minus plus 1. Anyway, okay, and this will give us, if we do some computations, this will be nothing else than lambda minus 2 and lambda minus 4. Well, clearly, the eigenvalues are distinct, are lambda 1 equals 2 and lambda 2 equals 4. And now their corresponding eigenvector, so let's take the first eigenvalue, lambda 2 equals 2. Anyway, its corresponding eigenvector is of the form, anyway, you know, you have to solve the system AX times equals lambda x, and I think I've done the computations here, so I'll just write it directly, and I'll leave the details to use. Of the form x1 will be okay, s negative s with s real number, right? And now if we take the second eigenvalue, lambda 2 equals 4, its corresponding eigenvector is of the form x2 will be t and with t real number. Okay, so these are the two eigenvectors corresponding to this eigenvalue, and for this we have this eigenvector, right? Okay. Well, it's quite clear what to do now. X1 dot x2 will be, guess what? St plus negative s times t, which will be st minus st, and this is nothing else than just 0. So x1 and x2 are orthogonal, and clearly the theorem is valid. Well, we have seen it applied on through this example. And now, well, we talked about okay. Now we want to talk about the main, the most important, the main thing of this lecture, which is the orthogonal diagonalization. Definition. And in fact, we would like to go back to the first question of this lecture, right? And we'll say that a matrix A is orthogonally diagonalizable when there exists an orthogonal matrix P such that P inverse times AP is a matrix D, where D is a diagonal matrix. And of course, since this matrix P is orthogonal, well, let me remind you that this is nothing else than just P transpose. So instead of computing the inverse and all this stuff, since you know that this is symmetric, whatever, then you just have to compute the transpose. Well, the following theorem will be fundamental for symmetric matrices. So theorem number 4, I think. And it says the following: let A be an n by n matrix then A is orthogonally diagonalizable right? And of course, and has real eigenvalues. If and only if A is symmetric. That's very important. That's the most important thing you need to know. So let's look at this theorem again. This is a very, very important theorem. Basically says that an orthogonally A is symmetric if and only if it's orthogonally diagonalizable. Well, that's the first thing, which is the main purpose of this lecture, is to show that if there exists another category of matrices that are diagonalizable, and this category of matrices, it's the category of symmetric matrices. And now let's see an example let's look at the theorem again. Now we'd like to see an example how to see which matrices are orthogonally diagonalizable. That is the question we want to answer. Which matrices are orthogonally diagonalizable? That is the question we want to answer. And let's give some examples, and we'll see which one. And let me consider the following matrices. Okay, I'm going to number from A1 will be 1, 1, 1, 1, 0, 1, 1, 1, 1. Okay, now let me take A2. Again, I'll take this 3 by 3. Let's say 5, 2, 1, 2, 1, 8, and negative 1, 8, 0. And now A3, we'll take this a 2 by 2 matrix. In fact, let me look that here. It's easy. And 2. Okay. 0, 0, let me take another one. 0, 0, 0, negative 2, for example. So which ones are orthogonally diagonalizable? Well, instead of, you can answer this question immediately, basically, based on the theorem above. Let me show that again, which says that a matrix A is orthogonally diagonalizable if and only if A is symmetric. So we want to see which are the symmetric ones. In other words, which matrices, which are the symmetric ones. That is the question. And now if you look at them, A1 is symmetric, it's quite clear. A1, let's see, A2, no, A2 is not. A1, and A4, right? These are the symmetric ones. So therefore, these are orthogonally diagonalizable, right? So this is how we see which matrices are orthogonally diagonalizable. But now we would like to see now how to diagonalize, how to orthogonally diagonalize such a matrix. Now we only know which one can be orthogonally diagonalizable, but we actually want to apply the procedure of orthogonal diagonalization. And we will talk about this. Orthogonal diagonalization of a symmetric matrix. And then we'll see some examples of this. Okay. Okay. Now, let's see. Let's consider, let A be an n by n matrix. Now, the first step, in fact, is to find all eigenvalues, of A and determine the multiplicity of each. Okay. The second step is for each eigenvalue, okay, for each eigenvalue, let's say of multiplicity 1, so for each eigenvalue of multiplicity 1, find a unit vector, a unit eigenvector, well, in fact, we can find any vector and normalize it. Let me point out this. We can actually, so we can find any eigenvector and normalize it. So at this point, it's quite clear what procedure we need to apply. And we will see some examples. And this is important. Find any eigenvector and normalize it. Okay. The third step is the following. Well, for each eigenvalue, and let's say in this case we have of multiplicity k, and this k is greater or equal than 2, each eigenvalue of multiplicity k, which is less than 2, we need to find a set of k linearly independent eigenvectors eigenvectors and we know that this is possible by a previous theorem. We have seen this, and we have a discussion here because we need to find a set of k linearly independent eigenvectors, and we want to see if this set is orthonormal or not. Now, if the set, if it is orthonormal, then it's great. But if the set is not orthonormal, then we apply the Gram-Schmidt orthonormalization procedure. Okay, and now the last step, the final step, and now using the results from previous two steps, from step 2 And step 3, okay, we produce an orthonormal set of n eigenvectors. Of n eigenvectors. That's what we want to produce at the end. Okay. And we want to use these eigenvectors, and moreover, we use these eigenvectors to form the columns of the matrix P. Okay. This matrix, the matrix P inverse times AP, which will be a diagonal, which will be equal to P transpose times AP, will be a diagonal matrix, will be equal to D, where D is a diagonal matrix. And guess what? The main diagonal entries, and let me point out this, the main diagonal entries of D are, guess what? The eigenvalues of A. Okay. Well, these are the 4 steps. It's pretty long, but it's quite clear what to do. Basically, we need to find the eigenvalue. We need to see the multiplicity of each eigenvalue, and to find their eigenvectors. If it's a unit eigenvector, then it's great. If not, we can normalize it. We know how to normalize a vector. We divide by its length. And then for each eigenvalue of multiplicity greater than 1, we find a set of k-linearly independent eigenvectors, right? And if the set is not orthonormal, then we apply the Gram-Schmidt to normalize it. And now we, at the final step, we produce that that set of orthonormal of n orthonormal eigenvectors. And we want to use this to form the columns of the matrix P, which will look like P inverse times AP, or that will be equal to P transpose times AP, and this will be the diagonal matrix D. And this diagonal matrix D will have its diagonal entries will be the eigenvalues of A. So now let's see an example. I'm going to take a 2x2 example, an easy example at first, and then we'll deal with the more complicated one. And I think after this, we're going to end the lecture. Let's see, example number 8, I think it is. So 2 more examples, and that's it. Let's formulate it in this way. Find a matrix P that orthogonally diagonalizes the matrix A, and let's pick a 2 by 2 matrix, a symmetric one, -2, 2, 2, 1. Of course, this is a 2 by 2, and A is symmetric. A is the same as A transpose. It's pretty easy to see that, right? Okay. Well, as you know, we apply these 4 steps, and let's do it. The first step is to find all eigenvalues of A and determine the multiplicity of each eigenvalue. Eigenvalue. Okay, let's do it. Step 1. Okay, let me write it like this. We want to find the eigenvalue. So to do that, we have to write a characteristic polynomial of A is given by P of lambda is the same as the determinant of lambda times the identity minus A, which will be nothing else than just the determinant of lambda plus 2, -2, -2, and lambda minus 1. And once we compute this, this will be lambda plus 2 times lambda minus 1 plus 4, which will give us, if you do the computations, this will be lambda plus 3 times lambda minus 2. Okay. So the eigenvalues of A are given by lambda 1 equals -3 and lambda 2 equals 2. Okay, step 2. For each eigenvalue, right, we want to find their corresponding eigenvector. For each eigenvalue, we find their corresponding eigenvector. Here we go. Let's see. For lambda 1 equals -3, we do the following. -3 times the identity minus A, which will be, okay, let me just look here by the computations. I'm not gonna, this would be -1, -2, -2, -4. Okay. And this, by elementary transformations, and I'll leave this to you as an exercise. You already know how to compute the eigenvectors of matrix. This, by elementary transformation, will look like in the following row reduced echelon form. This will look like the following matrix, okay? 1, 2, and 0, 0. Well, clear the eigenvectors. The eigenvector is this guy will be negative 2, 1. Anyway, yes, this will be the eigenvector. And now, let's see for the second one. For lambda 2 equals 2. Again, we have the following. We have 2 times the identity minus A. This will be the following matrix for negative 2, 1. And again, by elementary transformation, this will row reduce to the following matrix. 1, negative 1/2. Well, I hope my computations are correct. Okay, and 0, 0. And the eigenvector for this will be is 1, 2. Okay. And if we look at these two eigenvectors, right? Let's point out something here. The eigenvectors, let me write them in this way. Negative 2, 1, and 1, 2 form, it's quite clear they're orthogonal, or an orthogonal basis for R2. Right? Okay, and now we want to normalize them, right? Let's normalize them. And you know how to normalize. I'm going to denote it by this. So this P1 will be the first vector negative 1, 2, and divided by the norm of this vector 1, 2, and which will give us, let's see, the norm of 1, 4, 2, negative, okay. It will be negative 2 over square root of 5 and 1 over square root of 5. And the second one, right? Oh, whew. The second one, P2, will be vector 1, 2, and divided by the length of the vector 1, 2. And this will be nothing else than 1 over square root of 5 and 2 over square root of 5. Okay, great. And now let's apply step 3. So these are clearly normalized. Let me point out here. The length of P1 is the same as the length of P2, and is the same as the length is 1. Let's keep that in mind. Okay, and now step 3. Each of the eigenvalue, each eigenvalue has multiplicity 1. All right. So we go directly to step 3. Let's stop step 4. There is no point of applying the Gram-Schmidt orthonormalization procedure. In this case, we go to step 4. And in step 4, we said that we're going to use using P1 and P2 as columns as column vectors. We construct the matrix P. And let's write this matrix. Negative 2 over square root of 5 and 1 over square root of 5, the first column, right? And the second one will be 1 over square root of 5, 2 over square root of 5. So this is my matrix P. Well, I'll leave it to you as an exercise to check that that P is P orthogonally diagonalizes A. Well, how to do this is by finding P inverse times AP, which is nothing else than just P transpose times AP, right? So that's what we need to do. And then at the end of the day, once we do this computation, we have the following. In fact, let's write it. We have that P transpose times AP. Well, we can write this computation, and this will be negative 2 over square root of 5, 1 over square root of 5, 1 over square root of 5, 2 over square root of 5, okay, times the matrix A, which is negative 2, 2, 2, 1, and now times the matrix P, which is negative 2 over square root of 5, 1 over square root of 5, 1 over square root of 5, and 2 over square root of 5. Well, and if you do all these computations here, and I'll leave it to you as an exercise because I don't want to spend too much time on multiplying matrices, but anyway, according to my computations, this would be negative 3, 0, 0, 2. I hope I'm not mistaken. And voila, that's it. We found the matrix P that orthogonally diagonalizes A. And this is a diagonal matrix. Let's say this is D. And as you can see here, if you look at the main diagonal here, these are nothing else than just the eigenvalues of A. Okay, so this was the example, was a simple example. And now I want to have your attention for one more example. And I think we're going to end the lecture here. It's already a little bit too long. Example 9, and in this example, I want to use the Gram-Schmidt orthogonalization procedure. Anyway, so the same thing is to find a matrix P that orthogonally diagonalizes the matrix A. And this matrix A is given by the following. And it will be a 3 by 3. Okay, let's see. Okay, it will be 2, 2, negative 2, 2, negative 1, 4, negative 2, 4, 1. Again, this is a 3 by 3. So this is the problem. Again, the same question. The only difference is that this time we have a 3 by 3 matrix. Okay. Step 1. We need to find the eigenvalues. So the characteristic, again, the characteristic polynomial of A is given by PA of lambda is the determinant of lambda times the identity minus A. And this would be the following. In fact, I'm just going to write it directly. I don't want to lose time with this. This will be, if we compute everything together, the determinant will be, okay, lambda plus 6 times lambda minus 3 squared. Okay, great. The eigenvalues of A are lambda 1 equals -6 and lambda 2 equals 3, as you can obviously see. The thing is that one of them will have multiplicity 2, and well, that is lambda equals 3 will have its multiplicity will be 2, and the multiplicity of the first eigenvalue, which is -6, its multiplicity will be 1. So let's point out. Lambda 1 has multiplicity. Okay, lambda 1 equals -6 has multiplicity 1. And the second eigenvalue, lambda 2 equals 3, has multiplicity 2. Right? Okay. Okay. Now, step 2. Step 2, we want to find the eigenvectors for the two eigenvalues, and let's see that. So for lambda 1 equals -6. Okay, I'm just going to leave the eigenvector, the corresponding eigenvector is, let's call it V1, will be, oh my. Okay, so it will be 1, -2, and 2. And let's normalize this, which normalizes to the following. We divide by the length of this, and let's denote this by U1. So U1 will be V1 divided by the length of the normal this, which will give us, so this is So it will be 1/3, -2/3, and 2/3. Okay, so we normalize this. Let's keep this in mind, right? And now step 3, and here comes step 3, where we will apply the Gram-Schmidt the Gram-Schmidt procedure. Now, if we want to look at the two eigenvectors, so the eigenvalues. Let me point out this here. Step 2, not lambda 2 equals 3, right? And let's keep in mind it has multiplicity 2. Let's not forget that. We'll have 2 eigenvectors. So the 2 eigenvectors, the 2 corresponding eigenvectors for this are V2 will be 2, 1, 0, and V3 will be -2, 0, 1. Okay, so these are the corresponding eigenvectors, right? And now let's look at them. Let's look at V1. Let's look at this guy here, V2 and V3. What can you see about these guys? Well, if you look at them, well, the first question, are they orthogonal? Well, if you look at them, V1 is orthogonal to V2 and V3, right? We already knew this, right? There was this a previous theorem. We don't need to actually check this, but anyway. Well, V1 is orthogonal to V2 and V3, but V2 and V3 are not orthogonal to each other. But V2 and V3 are not orthogonal to each other. This is important. And now guess what? Well, let's orthogonalize them some way. And Gram-Schmidt procedure saves the day. And so we apply the Gram-Schmidt procedure to find two orthonormal eigenvectors for lambda 2 equals 3. Okay. Let's apply the Gram-Schmidt. So let's start with, so we look at vectors v2 and v3 because they're not orthogonal to each other. So let's look at them. So we're going to start, let's apply the Gram-Schmidt. So we're going to start with W is v2, which is, it is, what is it? 2, 1, 0. Where is it? Okay, 2, 1, 0. Okay. And now W3 will be V3 minus, you know, by the Gram-Schmidt procedure, this will be V3 dot W2 over W2 dot W2, and this will be nothing else. If we write this, if we do all these computations, again, let me check. Okay. So this will give us, okay. This will give us negative 2 over 2, 4 over 4, no, negative 2 over 5, 5 over 4 over 5, and 1. Okay. And now we normalize these vectors. We normalize these vectors, and we normalize them to the following. U2 we divide by, so it will be W2 divided by the length of W2, and this will be W2 is 2, 5, okay. It will be 2 over square root of 5, 1 over square root of 5, and 0. And now U3 will be U3 over the norm of U3, which will be equal to, so this would be, okay, negative 2 over 3 root 5, 4 over 3 root 5, 5 over 3 root 5. Okay, yeah. All right. And now this was step 3. I forgot to mention it. Step 3 here, when we apply the Gram-Schmidt. And now step 4. The final step is that the matrix P, let's form the matrix P, has the vectors, and this is U3, U2, and where is, U1 is here, right? Has these 3 vectors, has U1, U2, and U3 as its column vectors, right? Okay, let's write this amazing matrix. Oh my, let's do it. So U1 was, 1 over 3 now, okay. So it's 1/3, 2 over root 5, negative 2 over 3 root 5, negative 2/3, yeah, 1 over root 5, and 4 over 3 root 5, 2/3, 0, 5 over 3 root 5. Okay. This is my amazing matrix P, and guess what? I will leave it to you as an exercise to show, well, check that P inverse times AP is the same as P transpose times AP, and guess what? This will be, after some computations, finally this will give us -6, 0, 0, 0, 3, 0, and 0, 0, 3. Well, this is the matrix D, which is diagonal, and if you look at it, again, if you look at the main diagonal of this matrix, guess what? You will find the eigenvalues. Again, these are the eigenvalues of A. And that's it. It's over. And that's the end of the problem. Well, ladies and gentlemen, I think this concludes the entire course. I was planning to do something about the Jordan canonical form, but it's not included in the syllabus, so probably I should stop here. So thank you very much.